everyone. This video should be for chapter 14 about the sun. This is a little bit late, sorry about that. It's going to go with chapter 15. So, I'm going to go through these slides. It's a little bit extra from what the book tells you. I think here's some interesting stuff that we can find out of this. Of course, when we look at the sun, this is what we would see in visible light. This is looking out the window, looking at the sun. But we look at it in different forms. Some stuff we'll talk about you can already see here on various portions of the, right about there, you can see solar flares coming up there and here. And then you can see the modeling of sunspots and such. So there's stuff that we'll talk about that you can see here. You can see more here in UV light. You start to see essentially the effects of, you're seeing particles in the magnetic fields in these spots. These are not at the same time, of course. This happened to also be while there was a transit of Venus. You can see it's the black dot right there. And then there's some others, you can see during an eclipse or, with special equipment that can blot out, basically a disk that blots out the sun to simulate an eclipse. You can see the outer atmosphere. You can see the solar activity along the surface. And you can also look at the spectrum. All right, so this is the entire spectrum of the sun. But in particular, you can see things like helium, which, not going into too much detail, but helium was discovered in the solar spectrum before it was ever discovered on Earth. And they deduced that basically they were doing measurements to find all the materials on Earth that gave off spectrums. And then they found one that they'd never seen before. And they actually found it in oil wells where the helium comes up from radioactive material in the Earth and is effectively trapped in the empty space where the oil well's covered by rock. Right. So, as you'll learn in the textbook, we can talk about how the sun produces energy. Doing this 400 years ago, scientists thought maybe it was fire. And if you look at possible chemical reactions that can release energy versus how luminous and how massive the sun is, you find that would only work for about 10,000 years. Some people thought maybe it was just a gravitational contraction. And if you look at that, you realize that would work for 25 million years. So it's not easy sources of energy. But some nuclear process, something that would convert matter directly to energy, that would give you 10 billion years just using. That is almost certainly the conclusion that people would have to come to early 20th century, let's say. So how does this happen? Well, there's going to be nuclear reactions in the core of the sun that generate energy, and that energy radiates out eventually from us, and we'll go through that process. The key sort of thing going on in the sun that leaves the sun as it is and steadily working is what's called gravitational equilibrium. And the idea is that without something to press outwards, the sun would contract. Gravity would pull it together. That doesn't happen for things like the Earth because eventually chemical bonds in the material will hold up and stop the compression. And for planets like Jupiter And larger, that ends up being degeneracy pressure, which we talked about in the previous chapter. But for the sun, the contraction stops when nuclear fusion starts, and that produces energy that creates a pressure outwards. And so there's a balance. If there's less energy produced for some reason, the star contracts and it pushes the particles closer, causes more fusion, and pushes the star back out. And so the sun's day to day, year to year, stays the same size and keeps the uh, same rate of fusion and same energy production. Over longer periods of time, it does tend to produce slightly more energy as time goes on. It warms up, in a sense. But over short periods of time, there's this negative feedback between the gravitational contraction and the rate of fusion. So, interior, this is effectively your homework question number 5. If we start from the out, if we start with basic numbers, and then we start from the outside, the solar wind is just a flow of particles away from the surface of the sun. This is like particles leaving the atmosphere of a planet. Is they have enough energy to get pushed away, and they're pushed outwards, and they escape the gravitational hold of the sun and just flow through the solar system. It's not uniform. This is a picture of the distribution of it for most latitudes. It varies in speed, varies in composition. It's effectively particles from the corona, which will be sort of the outermost layer of the atmosphere. Fairly high temperature, but temperature is a measure of the average kinetic energy of a particle. There's just not a lot of particles there, so it doesn't have any substance to it. It doesn't, it's not highly energetic. It's just few particles moving fast. As we go inwards, as a corona during the eclipse, the corona is what you see during an eclipse. And then we can see the corona, and we can see holes in it. And we can see features where the solar wind is flowing and where magnetic fields trap particles. Oops, go back here. So active areas tend to have more particles form. So going further in, the chromosphere is, that's not what I wanted. The middle layer of the atmosphere, 10 to 100,000 degrees Kelvin. More particles, it's in the layer of the atmosphere. And we can measure by taking a spectrum, and this is what one of those spectrums might look like visibly. And you can identify the different elements. There's hydrogen and helium lines, and you can see streaks where the photosphere is showing through. And those streaks, will have both other elements in them that you can identify, and they'll also have, because it's a very hot object, it's glowing, they'll have a background intensity. The photosphere is what we would call the surface. It's the thing we can see, and it's about 6,000 degrees Kelvin. It's the thing that has all the features on it in that first image that we showed. And here's another one. Here, the little dot here is Mercury going in front of the sun, and this image is showing the photosphere at one particular wavelength. We can see the rotation of that surface. The rotation's about a month, approximately. There's different rotation speeds as you go around it. It's not perfect. It doesn't rotate exactly like a planet like a terrestrial planet would. All right, so as we go inwards, the convection zone is basically churning gas. Its energy is being transported through convection by rising and falling gases. And we can see by using Doppler measurements to deduce the motion of the interior, we can see where the convective cells are at the very top. You can see where they connect to the photosphere. Basically, the granularity of the photosphere. And we go further in the radiation zone. This is where energy is radiated as light. Now, this image is going to be very simplistic. We'll talk about that in a minute. And in the core is where the energy is produced. And what's going on is as you go into the sun, pressure has to increase, and only at the core is the conditions appropriate for nuclear fusion. Right, and here we can look the density as you go inwards. So starting at the surface, it's very low density, and as you go inwards towards the core, you very quickly get higher and higher and higher densities. Note this is a logarithmic scale, so the core is about 10 times denser than gold, roughly. About 100 times denser than water. As you go from temperature, again, from the surface on the right, you go inwards and you very quickly come up to a high temperature. But it's kind of a logarithmic increase as you go inwards. And then there's the rate at which temperature changes with pressure. Not sure that we get all that much out of it, but here. So, how does nuclear fusion occur? Well, all right. We take a moment here to describe fission. You take a big nucleus, you split. Fusion is taking small pieces and making a bigger piece. And so for fusion to occur, you have to put particles together, right? You have to build hydrogen into helium. But hydrogen is essentially protons. It's charged particles that repel each other. So to get close enough, what needs to happen is you need to get the particles that the strong nuclear force is stronger than the electrostatic force. And to do that, your particles need high energies, which means high temperature and high pressure. So you need the particle all crammed together, and you need them to be moving with very high speeds so that they can get close together even with the repulsion. The general idea is you take 4 hydrogens and you produce a helium. You produce some other particles, but the helium weighs less than the hydrogen and the other stuff that disappears, and you're left with extra energy. So the actual process is what's called proton chain. You build deuterium, which is a hydrogen isotope, out of protons. This produces extra particles that come off, neutrinos and photons. Neutrinos and positrons, so that your electric charge is conserved, and those things just disappear. The positrons are annihilated by electrons in the sun, and the neutrinos don't interact with anything. The deuterium will fuse with another proton, and so this makes helium, but not quite what we want. It's another isotope. And then those 2 isotopes fuse and form the actual helium-4 nuclei. And what we start off with is 6 protons, and we're left with 2 protons and helium. And we produce some extra stuff, and we produce light. And the light's produced when the deuterium fuses. That's where the photons escape from. So we'll go through the details of it in smaller steps. And just as what you start with is just a little bit more massive than the stuff that you end up with. And that difference in mass is converted to energy at the gamma rays. We talked about regulating the temperature. That is through this feedback cycle. We talked about gravitational contraction. Um, and when you have a change in the temperature, that's going to increase or decrease the fusion rate, which changes the pressure in the core, which causes either expansion or contraction. The idea is that whatever change you have results in a change in the core that restores the original conditions. It's a negative feedback. All right, so we've produced some energy. That energy controls effectively the size of the sun. It holds everything together. How does that energy get out of the sun? Because there's clearly some coming to us. How does it get out of the sun? Well, once it's produced in the core, it effectively gets out of the core fairly fast. But the cooler outer layers will absorb the photon. They have capacity to absorb it. And so it heats the outer layers up. And those outer layers will eventually re-emit photons. But those photons aren't emitted outwards, they're emitted in random directions. It takes a while for the energy produced in the core to leak out of the sun. First, it leaks out through the radiation zone. Once it gets from the radiation zone to the convective zone, the hot gases can absorb the light, but they don't re-emit the light. They can absorb and hold the energy. So they're effectively opaque. So it insulates the interior, and that means you have a heat source on the bottom of the convective zone and a place for that heat to go at the top surface. And so you have convection start. So the energy goes through these layers, effectively radiates through the core, and then randomly radiates through the radiative zone. And then there's convection through the convective zone. And so eventually the hot gases get to the top of the convection cells at the photosphere, and they can then radiate light outwards. So you can see where on the photosphere where hot gas is reaching the surface, and it glows more because it's hotter. So we have to deduce how the workings inside the sun is going, and of course one way is to look at the surface and to look at the patterns that we see and let that tell us about what's going on in the interior. This is what's called helioseismology, looking at the surface to figure out the interior. Effectively, Doppler shifts give us some information. And it works reasonably well. We can model the interior pretty well and match it to the data. The other thing we can do is take particles that come from the core directly. All right, and so of the stuff that's produced, the massive particles stay behind. Helium and hydrogen stay in the core. The positrons all get annihilated. The gamma rays do this random walk, so it gives us very delayed information. But the neutrinos, once they're produced, they leave. They get created and they go directly through the sun. It's completely transparent to them. And the problem is, if we can measure it, it would tell us about what's going on in the core, but it's completely transparent to us as well. We have to find ways of detecting them. And so a reasonable way people started with was taking dry cleaning fluid, which had lots of chlorine in it, burying it underground so it doesn't get affected by anything else, and when neutrinos could come in and interact and produce argon, which is a gas. And this would let you detect tens of atoms over weeks. And this came up with a problem, is they had an idea of how many particles could be detected, and they saw about a third of them, which means either the sun was not producing energy the way we thought, or something's going on with our experiment. And so some different versions of the experiment um, kept finding this problem of there's not enough neutrinos. And we could definitely model what's going on through this helioseismology. We could figure out reasonable ideas for temperature, impression, and fusion rate. It had to be something wrong with the experiment. And it turns out, if we go back to the description here, we're talking about one type of neutrino. We talked about in the previous chapter that there are three types that go along with the only finds one type of neutrino. What if they can change form? And we think we've been able to deduce that they do change forms, and there's basically an equal mix between the sun and the earth of the three types of neutrinos, and so we only detect a third of them. Right. So all this other stuff on the surface that we see, solar activity, it's kind of like weather. It's stuff happening in the sun's atmosphere. We get sunspots, we get solar flares, solar prominences. All of these things are effectively magnetic fields causing particles to move through the atmosphere and do interesting stuff. Sunspots. They're darker areas on the surface of the sun. Darker areas generally are lower temperature. They don't produce as much light, and that's what we see, is that they're cooler areas on the surface of the sun. And the reason they're cooler is that there's a bunch of strong magnetic fields in those locations. And we can observe that. So something called the Zeeman effect is when you have spectral lines, they occur based on atomic transitions from one level to another. But if you have a very strong magnetic field, it can separate out the particles that can go in those atomic levels based on their spin. And so you can see these broadened and divided out uh, spectral lines because if there's a strong magnetic field in the sunspot. So magnetic fields are going to cause particles effectively to spiral around them, and so they tend to trap charged particles and make them flow in their direction. And so you end up with loops that connect the sunspot pairs, and you'll get hot gas trapped within those looped lines. And in more stronger activity gives solar flares, which throws matter out into the atmosphere, and eventually you get bursts of particles and X-rays that fly out into space. And so you'll see different after flares. You see the magnetic field and particles that are remaining in the loops. And you'll see even larger loops, what are called prominences, that do effectively the same thing. Right? And you'll see places where there's bright areas here in X-rays, places where magnetic fields have trapped a lot of hot gas. And then the biggest version is what's called a coronal mass ejection. It's basically an eruption that throws a bunch of stuff out. And of course, we would think, well, this is weather occurring on the sun. It doesn't affect us, but it can. It can affect us. And the idea is that we get these bursts of charged particles and X-rays and such out through the solar system. They take time to get to us, but these particles, more of them will come into Earth and be trapped in the Earth's magnetic fields. So they do things like auroras, but they also do things like disrupt the electrical grid or disable communication. Anything that relies on radio transmission can tend to be really screwed up by very active charged particles in the Earth's magnetic fields. Activity vary with time. Once we realized that it was possible, and we realized it's something like the 1700s, realized the surface of the sun varied, we could track, basically counting the number of sunspots and graphing where they appeared. And what we see is that there's a pattern. Every 11 years or so, we see a minimum in the number of sunspots, and then they go back up. Is that the sun waxes and wanes, in a sense. And when there's a bunch of sunspots, we can see that they're produced at high latitudes, and then there's more of them towards the equator, is that they follow this kind of shift upper latitudes down to the equator before they go away again. And so we've tracked this since about 1750 up to the current day. And of course, the numbers of sunspots will vary in each cycle. Sometimes you'll have lots more in a cycle, and sometimes you'll have, recently we've had very low sunspot numbers, which have been bad for me teaching this class. But in general, more sunspots means more of other sorts of activity as well. This cycle has something to do with the rotation of the sun and its magnetic field. Effectively, the equator rotates a bit faster than the poles. And so the magnetic field gets twisted. It gets bound up a bit. It gets this sort of deformed shape. And then eventually it rights itself again and then comes back to this twisted shape. So that concludes chapter 14. We'll start the next video immediately off of stars. As you're going through this, if you have questions on the homework, please email me, let me know. Otherwise, hopefully the stuff seems pretty straightforward. It's just talking about how the sun works and eventually how stars will work.